Good morning, everybody. Today we will continue with X-ray reflectivity. This is very important, very useful method for scientific applications and also for industrial applications. By using this method, you can get the thickness, roughness, and density information of ultra-thin films in industrial applications and also scientific applications for hot topics in physics, in material science. Very important, very useful method. So today we will learn the details of the X-ray reflectivity, and we will have some real examples with real samples. So what is the aim? Why we are using X-ray reflectivity? We can determine the electron density of the thin films. We can determine the layer thicknesses of thin films. And we can also determine interface and surface roughness of the thin films. In addition to that, if you have a multi-layer system, let me draw a multi-layer here. Let's consider this is a multi-layer thin film system. This is the silicon substrate. And here we have iron, for example, let's say 10 nanometer thickness. And here we have, let's say, iridium manganese, 20 nanometer. And here we have chromium, let's say 3 nanometer. And here we have platinum, let's say 3 nanometer. So by using this method, by using X-ray reflectivity, you can even determine the individual thicknesses of each layer, okay? You can determine the thickness of the platinum here, thickness of the chromium, thickness of the iridium manganese, thickness of the iron here, okay? Independently. So this is very powerful method. In addition to that, you can determine the density of the platinum, density of the chromium, density of the iridium manganese, density of the iron. So why this is important? Look at this one. So here we have iridium manganese. Let's consider that iridium is 0.20 and manganese is 0.80, let's say. Okay. So if you have pure iridium in this layer, pure iridium, then it has certain electron density. If you have pure manganese, it has different electron density. Okay? If you have 50% iridium, 50% manganese, then you have different electron density. If you have 20% iridium, 80% manganese, you have different electron density. So then by using this property of the X-ray reflectivity method, you can even determine the concentration within this layer, okay, concentrations of iridium and manganese. So very powerful method. We will go into detail later on. As I told you, we can determine the layer thickness of each layer in a multi-layered system. And so in reality, we have roughness at the surface of the thin films. And in addition to that, at the interfaces between the layers, we also have roughness. Okay, so this interface and surface roughness of the substrate and the layers in a multi-layered system can also be determined by using X-ray reflectivity method. The main advantage is it is non-destructive. Okay, you do not destroy your sample. And layer thicknesses between 1 angstrom and 400 nanometer can be determined. So here I'm talking about 1 angstrom layer thickness, okay? So this can be done. There are several publications in the literature related to this precise determination of the thickness in multi-layered systems by using X-ray reflectivity, and the roughness at the surface of the thin films and also at the interfaces also can be determined by using this method. Between roughnesses between 0 to 2 nanometer or 20 angstrom can be determined by using this X-ray reflectivity method. Okay, what about the X-ray reflectivity measurement setup? So setup is exactly same as the X-ray diffraction setup. So if you have X-ray diffraction instrument in your laboratory, you can also carry out X-ray reflectivity experiments. Of course, if you have very nice goniometer, so you need very precise, very nice goniometer. Here, there is an X-ray tube, okay, on the left side, and these are the optics. This is the sample here. Okay, sample is located here, and here we have an X-ray detector. Detector is waiting here, so these are also optics. Here we have K-beta filter. We have discussed this one in previous lectures. Okay, so X-rays are coming from the X-ray tube and they go to the X-ray detector. This theta is the sample angle, this 2 theta is the detector angle. We have also discussed all the things in the X-ray diffraction part. So today I will not go into detail. So what you have learned in X-ray diffraction is valid here related to the setup, okay? You must have very nice goniometer. You should able to change the theta and also 2 theta precisely in X-ray reflectivity experiments. So, but before you start for the experiments, you have to align the sample according to the incoming beam. This part is very important both in X-ray reflectivity experiments and also in X-ray diffraction experiments. Actually, if you are dealing with optics, if you are dealing with X-rays or photons and samples, okay, if you are carrying out experiments by using the optical methods, you must be very careful with the sample alignment and optical alignments, okay? So now I will go into a little bit detail related to the sample alignment in X-ray reflectivity measurements. So what is the sample alignment? Here you see a detector. This yellow one is detector, let's consider. And this detector is connected to the goniometer, so you can move it up and down. And here we have another goniometer, then we will put the sample here. So this sample can also be moved by using goniometer. Now I will start the animation. So now this green one is our sample, okay? This red one is the beam, which is coming from the X-ray source. Let's consider X-ray source is located here. Okay, then this is our sample, green one, and this is the sample holder here. So now the sample is out of the beam, and these X-rays are directly going to the detector, okay? Then you change the position of the detector and you are searching for the best position for the detector. After that step, let me go back. So here we are changing the position of the detector and we are looking for the best position for the detector. I will go into detail. I will explain step by step. But first of all, I would like to show you the complete procedure. So now you move the sample in to cut the half of the beam. Then the sample is in now and you cut the half of the beam and you do sample scan to make the X-ray beam exactly parallel to the sample surface here. Then another sample scan, another half intensity scan. And you go to higher angles, another sample scan here, and chi scan. And finally, sample alignment is finished. And the sample and diffractometer are ready for the X-ray reflectivity measurements. Actually, before the X-ray diffraction experiments, you also have to carry out this procedure, okay? So in old machines, in the X-ray diffractometers, for example, the X-ray diffractometers in the synchrotron light sources, you have to carry out or you have to perform all these steps by yourself, okay? But most commercially available instruments can do this procedure automatically, okay? So this is the diffractometer, and this is the sample, and you align your sample. Your sample must be perfectly parallel to the incoming beam, and you should cut the half of the beam. So now I will go into detail step by step. So here you have seen many different steps, okay? Many different steps. So these steps have been carried out automatically by the instrument, but what is the meaning of each step and what they tell us, okay? So now I will explain step by step. The first step is the determination of the direct beam, okay? So how to do that? It is done with detector scan. So how to determine the direct beam by performing detector scan. So what is the meaning of this? Here we have an X-ray source on the right side. Let's consider X-ray source. And here we have a detector. This is the active area of the detector. And what is the detector scan? We have X-rays produced by X-ray source, and they come to the active area of the detector. Sometimes detector position is not correct. Let me show you with different colors. So detector is staying here, for example. Or sometimes detector is staying here. Okay, so in such conditions, produced X-rays can not enter into the active area of the detector, or sometimes it can be like this. This is the detector active area. Some part of the incoming X-rays enter into the detector, but other parts cannot enter. So the detector position is not correct. So what to do? We have to carry out detector scan. Okay, we have to carry out detector scan. So what is the meaning of detector scan? We change the position of the detector. So we move detector in this direction or in this direction. Okay, how to do that? We have to move detector into theta axis. This is the intensity goes to detector. So if the detector is staying at the correct position, then you should see this type of behavior. If the detector is staying exactly at the right position, you should see very high intensity at 0, okay? If you move the detector to the positive side, up a little bit, the active area of the detector will move up, and then less X-ray photons come to the active area of the detector, then the intensity at the detector will drop. And if you go back and move to the negative side, then we will see the symmetric curve, the same mechanism, okay, which we have observed in the positive side. But if the detector is not staying at the right position, for example, if the detector is staying like this, let's say 0.2 degrees, okay? You cannot judge this 0.2 degrees by eye, okay? So this is the position of the detector. What to do? You have to move this one down, okay? So then you move the detector to this position, 0.2 degrees. You send the command to the computer, move 2 theta to 0.2 degrees. Now detector is located in 0.2 degrees where we see the highest intensity at the detector. Then we set to theta to 0. Okay, then we have the correct position for the detector. If you carry out this experiments again, to theta intensity, since we have corrected the position, we will have a symmetric curve around 0. This is 0. Okay, we have shifted this curve to the left side by changing the position of the detector. Now we have correct position of the detector. Detector is staying like this. This is the active area of the detector, and this is the 0 position of the detector. So all incoming X-rays, I mean direct beam, intensity 0, directly goes to the active area of the detector. Detector is staying at the right position. Do you have any question here? This is the first step.
Hocam, here we be able to move just the detector. I mean, the X-ray source, we cannot move it, right?
Yes, let's consider in the synchrotron light sources, you cannot move the beamline, okay? You cannot move the beamline. X-ray source is staying at the right position. But in some commercial X-ray diffractometers, X-ray source can also be moved. I have shown you some pictures of such X-ray diffractometers, so you can both manipulate the position of the X-ray source and X-ray detector. But in such cases, of course, at the beginning, you have to send the X-ray source to the 0 position, and then you should start with this alignment procedure. Okay, I'm just here talking about the sample alignment, but also the optics in front of the X-ray source and also in front of the X-ray detector must be aligned. But I will not go into detail with these things because all the procedure has been done automatically by the instruments.
Okay.
So now direct beam is okay. We produce X-rays in the X-ray source and they directly go to the active area of the detector. But what about the sample? We don't have sample here. Now the second step. The second step is cutting half of the beam, half intensity. This is the full intensity I0 direct beam, and we need half intensity. So how to cut the half of the intensity? Here again, the detector is staying here. Let me draw the detector again. And this is the active area of the detector. And here we have the X-ray source exactly at the same position. And the produced X-rays, X-ray beam goes directly to the active area of the detector. This is direct beam, full intensity. So I need half intensity, I0 half. So in order to get this one, we have to move the sample in. Let's consider this is our sample. It is located here, and we have to move this sample into the beam, and we have to cut the half of the intensity. So how to do that? Just move the sample in, and then this is the sample, and look at this part. Now, half of the intensity is blocked by the sample, okay? At the beginning, the intensity at the detector was I0, now I have I0 half. So this move can also be done by goniometer, okay? So what is the mechanism? The mechanism is like this. This is the time in second, and this is the intensity at the detector. So when you move the sample down, so here, here, at this position, the intensity will be I0, okay? Because the sample does not cut the intensity. So we have full intensity at the detector. Whenever the sample starts to enter into the beam goes down. And if you move the sample completely into the beam, then you can completely cut the beam. So then intensity will go to 0. But we need half intensity. So you move back the sample a little bit, then intensity increases. Here at this point, we have half intensity. Okay, I0 half. So why we need this one? Why we are doing this? If you don't have the sample within the beam, you cannot investigate your sample. This method, X-ray reflectivity, is used to investigate the sample, right? If you don't have the sample here, then you cannot investigate it. But you have half intensity. So what about the beam and sample surface? Actually, they must be exactly parallel to each other. So let me show you the surface of the sample here. This is the sample, let's consider, okay? The surface of the sample must be exactly parallel to the beam, okay? So sometimes what happens, let me show you with another color after cleaning this part. Sometimes you cut the half of the intensity, but the sample is staying like this. So half of the intensity goes to the detector. Okay, this second step is satisfied, but the sample surface is not parallel to the beam. Okay, but if this angle here between the beam and sample is very small, you cannot see it by eye. Okay, I'm talking about 0.1 degrees, 0.01 degrees, something like this. Okay, in this case, you have to move the sample in these directions, in positive and negative directions. Okay, so you have to carry out sample scan. Okay, so what is sample scan? It is like detector scan. The X-ray source is fixed at fixed position. X-ray detector is at fixed position, and we move the sample. So what to do? What is the sample scan? This is the theta angle, okay, sample angle. This is the 0, and this is the intensity. Normally, if the sample is staying exactly parallel to the surface, then here we have I0, half intensity, because we cut the half of the intensity. So if you move to the positive side, the intensity will go down. Okay, let's consider that the sample is exactly parallel to the beam. Let me show you what will happen. Let's consider this is positive direction. I am moving the sample in this direction. So then I am rotating the sample. Just consider like this. After certain angle, the sample will be like this. And what do you see here? No intensity can go to the detector, okay? For this reason, if you increase this theta angle in the positive direction, then intensity goes down and finally goes to 0, because no intensity can go to the detector. And if you come back again to the old position, let's consider it is perfectly parallel to the beam. At 0 position, again, half of the beam goes to the detector. Then let's move the sample in negative direction, then you will see more or less the same behavior. What happens to the shape of the sample? Then the sample will be like this. So again, we cut the intensity. and the intensity at the detector is 0, okay? So look at the intensity. This is the intensity axis. So if you go to negative side, if you go to positive side, intensity will drop. And if the sample is exactly parallel to the beam, then we have the maximum intensity when the angle is 0, when the sample is exactly parallel to the beam. But sometimes the sample is not exactly parallel to the beam, as I have told you. The sample is staying like this. Let's consider that this angle is very small and you cannot judge it by eye. Then half of the intensity goes to the detector, but the sample surface is not parallel to the beam. Then what about the signal? The signal here will be like this. Let's say this is 0.1 degree. So what to do? You have to say move theta to 0.1, set theta to 0, okay? Where you see the maximum intensity. And then now you have correct position for the sample, okay? But this is not enough. This was the third step. If the sample is not parallel to the incoming beam, a sample scan is performed. So this was the third step, sample scan. Okay, we have done sample scan, and then we realized that the sample is not perfectly parallel to the beam. So then we moved the sample to the correct position. But what happens? Let me draw another figure here. So what do you see here? We have done sample scan and we have corrected the position of the sample. Now it is parallel to the beam. But what do you see here? Now the intensity at the detector is bigger than the half intensity. So after correction the position of the sample, then the sample is moved a little bit down, let's say, okay? Then more intensity goes to the detector. Now again, I have to repeat the sample in and out, and we have to find the half intensity, okay? So first step, find the half intensity again, okay? We will move sample up and down again, and we will look for the half intensity. Okay, we will repeat this second step. Okay, so then when we have the half intensity, let's say here we have the half intensity. You move the sample in, and then we cut the half of the beam. Now we have half intensity at the detector. And we think that the sample is exactly parallel to the beam, but it is better to repeat here the sample scan, okay? So you change the position of the sample like this in positive and negative direction again. You carry out another sample scan. If you got this type of behavior in the graph, in the intensity versus theta graph, like this is the 0, okay, then it means that the sample is exactly at staying 0 and it is perfectly parallel to the X-ray beam, and we have half intensity at the detector. As a last step, what we are doing, this is the position of the X-ray source. This is the position of the detector, and this is the position of the sample. Now we have some certain theta angle here, certain theta angle here, okay? So we have changed the position of the 2 theta, we have changed the position of the detector. Now the detector is staying another 2 theta angle, but this is very small angle, let's say 2 degrees, something like this. and theta is 1 degree, okay? Actually, it must be half of the 2 theta, okay? So then at this condition, we repeat the sample scan again, okay? We repeat this procedure. Now the sample scan must be like this. This is the theta. So let's consider this is 2 and this is 0, okay? And if the result is like this, then the position of sample is correct, then you can start for the experiments. But sometimes, again, this position can be like this or like this. It can be shifted to the left or right side. So now here we have, let's say, 0.9, and here, let's say, we have 1.1, okay? So then again, you have to say, for example, just blue case, you have to say move theta to 1.1, then set theta to 1, okay? Then you have the right position, then you can start for the experiments. These are the steps for the sample alignment in X-ray reflectivity and X-ray diffraction experiments. In addition to the scattering experiments, in absorption experiments, for example, X-ray resonant magnetic scattering, this procedure is also repeated, okay, to get the good results. And let me remind you that without doing these steps, you cannot get meaningful results in X-ray reflectivity experiments. Even in other optical methods, if you are doing experiments with the optical methods, if you are using the optics, the optical alignment, the sample alignment are very important. So now let me go back to the transparency. We have learned all the steps in the sample alignment, okay? So as a final step, the sample scan is repeated at higher angles. Then the sample is ready for measurements, okay? So as I told you, all these steps which we have discussed here are done by the instruments automatically in commercial instruments, okay? Here, I will repeat this animation and this will be more meaningful than before. Okay, now look at the animation. Now the sample is out. We don't have the sample in the system. Okay, and this beam comes from the X-ray source and goes directly to the detector here. And I don't know whether the position of the detector is correct or not. Then I will carry out detector scan. Look at this figure here. This one, this is the position of the detector, 2 theta, and this is the intensity. Okay, now I continue. We change the position of the detector and intensity changes. Okay, if you're far from the incoming X-ray, intensity goes down. If the incoming X-rays can reach to the active area of the detector, we have very high intensity here at this position. Okay, now the detector position is good. Now we have found the correct position for the detector, and we will move the sample in and we will look for the half intensity. Okay, so then the sample moves in. Okay, so look at this one. This axis again intensity, but this one is time. Okay, and let's have a look here. Here at this position, intensity is maximum, and whenever we move the sample into the beam, then intensity goes down, you see? And now intensity is 0 because we cut the whole beam, which is coming from the X-ray source, so no X-ray can reach to the active area of the detector. Then the intensity at the detector is 0, okay? But half intensity is required. Now we have the half intensity, okay? We have just cut the half of the intensity, and then I have to look whether the surface of the sample is perfectly parallel to the X-ray beam or not. Now we will carry out theta scan. This axis will be position of the sample. This is the intensity again. Now this is the theta scan. And after this step, we have again half intensity. Okay, again theta scan. And now we are going higher angles. Now the detector is not staying at 0. Let's say it is staying at 4 degrees or 2 degrees. And the sample is staying at the half of the 2 theta. If detector is staying 4 degrees, then the sample is staying 2 degrees, okay? Then we will carry out theta scan here at this position. Theta scan, okay? And if the position is correct, we are doing another scan, chi scan. This is required to exactly make the sample surface parallel to the beam. Then after this step, you go to the starting point, you have the half intensity, sample is perfectly parallel to the X-ray beam, and you can start for the experiment. This was not the experiment, this was not the measurement. This is just important step before the measurement, okay? This is the sample alignment in X-ray reflectivity experiments, and with this one, the alignment is finished. Okay, then let me continue with the informations which we can get from a reflectivity curve. Here we have a real X-ray reflectivity curve. Okay, this is the intensity at the detector, and this is the 2 theta angle position of the detector. So this one, this is the sample. This is the X-ray source. X-rays are coming with some certain theta angle, and they go to detector with the same theta angle, or with this 2 theta detector angle. And we know that this theta incident angle is always half of the detector angle. So X-rays are coming to the detector from the sample, and intensity is recorded at the detector. So here we have on the left side, on the Y scale, we have intensity, and here we have the position of the detector. So we change the position of the detector and sample simultaneously. We change the theta, and we also change the position of the 2 theta by ensuring this condition. Okay, so this is the measurement. Then we have this result. This is the X-ray reflectivity data. This is characteristic for each sample, okay? So for another sample with another layers and thicknesses, you will get completely different X-ray reflectivity curve. So then this is the result. What do you see here? We have many features here, okay? So here intensity is huge, and here intensity goes down. And then after this step, intensity is going down by following this way, okay? But we have features here. So these features tell us a lot about the sample and about the layers of the films within this sample. So look at here, for example, here we have a plateau, which is not clear here, but in simulations I can show you much better representation. Let's consider here we have a plateau, and this plateau gives us information about the sample size, roughness, absorption, and also properties of the instrument. And here we have a critical angle. Look at this 2 theta angle or theta angle. At this angle, the intensity suddenly decreases, okay? Sharp decrease we have here. This is called as critical angle, where this sharp decrease happens in the intensity, and this critical angle is related to the density of the material. And here we have oscillations, okay, and we have distance between the oscillations, okay. So this distance between the oscillations gives us information about the layer thickness, film thickness. And here we have amplitude, okay. amplitude of the oscillations. This amplitude gives us information about the roughness, interface quality, density variations, and resolution of the instrument. And another feature here, the shape of this figure, the shape of this curve gives us roughness and density information. So if you change the roughness of the material, if you change the density of material, then the shape of this curve will be different. If you change the roughness, interface quality, density variations, and also resolution of the instrument, you will have different amplitudes. If you have different thicknesses, you will have different distances between the oscillations. Okay? If you have different material, if you have different density, then you will have different critical angle. So depending on the sample, depending on the layers within the sample, you will get different X-ray reflectivity curve, and this background signal is related to the instrument. So within the forthcoming transparencies, I will discuss all the details of this features in a reflectivity curve. In addition to that, I will discuss the shape of this general behavior of this intensity. So at the beginning, we have huge intensity, then this intensity goes down with this behavior. Okay, so we will investigate this behavior theoretically in the forthcoming part, and we will try to find a relation between critical angle and electron density by using the Fresnel reflection. Okay, let me continue with the Fresnel reflection in order to calculate the relation between critical angle and electron density, and also in order to explain the behavior of the reflectivity curve as a function of the 2 theta angle. So here we have a sample, and this sample has refractive index of n. Okay, this n is given with this expression you remember from the optics lecture, 1 minus delta minus I beta. And this is the incoming X-ray beam. This is the reflected X-ray beam. This is the incident angle theta. This is the reflection angle theta. This is the transmission angle, theta transmission. Okay, so some part of the X-ray beam is reflected and goes to the detector, and some part of the incoming beam enters into the material and propagates with some certain angle within the material. And this is the refractive index of the air, which we take 1. So what about the refractive index of the medium n here? It contains delta and beta. As we have discussed in the previous lectures in X-ray matter interaction, this delta is related to the scattering mechanisms, and this imaginary part includes beta is related to the absorption. And again, as we have discussed in the X-ray matter interaction part, we have delta, which is given with lambda square over 2 pi. And here we have classical electron radius. Here we have electron density. Okay, this refractive index includes the electron density of this material. And beta includes wavelength of the incoming X-ray beam over 4 pi and absorption coefficient of the material. Okay, so what about the electron density? Electron density you can consider like this: how many electrons we have within this material. Okay, this electron density has this type of definition: Z times N. N is the number of atoms in unit volume. In a unit volume, how many atoms do we have within this material? And this Z is the number of electrons per atom. Okay, so then you can calculate number of electrons in a unit volume. This is electron density. This N, number of atoms in unit volume, is given with this expression. You remember this expression from the previous courses in physics. This is the Avogadro number, this is the density of the material, and this is the atomic weight. What do you see here? That the electron density is proportional to the density of the material, So this is characteristic for each element, each material, okay? So then let's continue. For a specular reflection, theta incident is equal to theta reflection. So here we have theta angle and here we have theta angle, and they are equal to each other in case of specular reflection, okay? Using Snell-Descartes' law, we have this relation: n times cosine theta incident is equal to n medium times cosine theta transmission. N air times cosine theta incident is equal to n medium times cosine theta transmission. We are using hard X-rays. So in case of hard X-rays, the absorptions are very small compared to the scattering, okay? So then this absorption part can be neglected. So then we have here n, which is equal to 1 minus delta. Here we have n. Just put this n here. And here we have n air. N air is 1. Just put 1 here. Then finally, this Snell-Descartes' law can be written in this form. Cosine theta incident is equal to 1 minus delta. This is n medium times cosine theta transmission. If this incident angle is very, very small, then all incoming X-rays can be reflected from the material surface, which is called as total external reflection, and no X-ray can enter into the material. In this case, theta transmission is 0, okay? There is no transmission. All X-rays, all incoming X-rays are reflected from the surface of the material. But if this incident angle is very small, okay, this is total external reflection. This is like you throw a stone on the surface of the lake or water with very small angle, okay? This is total external reflection. So on the left side, we have cosine theta incident. On the right side, we have 1 minus delta times cosine theta transmission. Cosine theta transmission is 1 for this special condition for very small incoming angle, very small incident angle. So then, which is equal to 1 minus delta. So instead of this theta incident, I can take theta critical, because I'm talking about special condition for the theta incident. So here we have theta incident, okay? And I am talking about critical angle for the theta incident. Below this critical angle, all the X-rays are reflected from the surface of the sample and total external reflection occurs. Okay, then let me continue. Here we have cosine theta critical. And what I have told you that this critical angle is very small, okay? Very small angle. And we have total external reflection from the surface. So since this angle is very small, cosine theta critical can be written with this form by using the Taylor series. If the angle is very small, then cosine theta is given with 1 minus theta critical square over 2. Okay. Then what about the cosine theta critical? Cosine theta critical is equal to 1 minus delta. So then just take this one, put it there to the right side, and cosine theta critical can be written in this form by using the Taylor series. Then we have this expression. What do you see here? This will cancel. This one, this will cancel. This one. Then finally, we have this expression. Theta critical square is equal to 2 delta. This is critical angle. This is delta. What was delta? Delta is this one. Delta includes electron density, right? And here I have found a relation between critical angle and electron density. Look at the X-ray reflectivity curve here. This was the critical angle where the X-ray intensity starts to decrease. This is critical angle, and this critical angle gives us information about the density of the material. Okay, now we have found this one theoretically. So critical angle is related to the electron density of the material. And what happens at this critical angle? Let me talk about this one. Let's consider this is the X-ray reflectivity curve. This is the intensity, this is the 2 theta, and this is the critical angle. Below the critical angle, we have full intensity at the detector. All the intensity goes to the detector, okay? We have total external reflection. But if you increase the angle, if the incident angle is bigger than critical angle, then let's say theta is bigger than critical angle, then this incoming X-rays start to penetrate into the material, and then we have theta transmission. So then some part of the incoming X-rays are lost within the material. Less photon goes to the detector in that condition, okay? So then intensity at the detector decreases at this angle, and then after this angle we have this type of behavior. Okay, this is the relation between the critical angle and electron density. So depending on the electron density, this critical angle changes. So it depends on the material, it depends on the layers within the sample. So this is very important for real applications. I will show you some examples. Then let me explain why we have this type of behavior in the X-ray reflectivity curve. Why intensity goes down with this relation by changing the 2 theta angle. So here I will try to explain this part by using the Fresnel reflection again. Again, here we have the same figure, theta incident, theta reflection, theta transmission. Here we have n air, which is equal to 1. Here we have n medium, okay? And this is the Fresnel reflection coefficient, R. You have learned this one in the previous courses, but I will go into detail a little bit. This Fresnel reflection coefficient is given with X-ray is coming from this medium, air medium, and enters into the material medium, okay? And air times sinus theta incident minus n medium times sinus theta transmission over n air sinus theta incident plus n medium sinus theta transmission. So what about n air and n air here? They are 1, okay? And here I have n medium. I can use n medium formula, 1 minus delta minus I beta. You can neglect absorptions again, or you can keep them within the equation. We will do that. And here we have sinus theta transmission. What is theta transmission? I know what is theta incident. I tell the computer to move the goniometer to this sample angle, theta incident. But what about theta transmission? It is not possible. It is impossible to measure this theta transmission. Okay, I can measure this one, I can measure this one, but this one cannot be measured. So within this equation, in the Fresnel reflection coefficient, I should get rid of this theta transmission. So this equation must not include this theta transmission term. So how to get rid of this theta transmission? Just use Snell-Descartes law in this Fresnel reflection coefficient. We know that n cosine theta incident is equal to n medium cosine theta transmission. So here we have theta transmission. Take theta transmission from this expression and put it there. So then we will have only theta incident within this Fresnel reflection coefficient. Did you understand this step?
Yes, why do we need to find this theta transmission.
We don't need theta transmission. I would like to solve the Fresnel reflection coefficient because here we have a detector and detector records the intensity. And this is also called as reflection, okay? Reflection from the surface or intensity recorded at the detector. And I am looking for the behavior of the X-ray reflectivity curve. Why this reflectivity, why this intensity decreases with this 2 theta, okay? So I would like to search this one. So this R is given with this one, Fresnel reflection coefficient, okay? So I have to solve the Fresnel reflection coefficient and then I can find the reflectivity or intensity as a function of the theta, okay? I would like to explain the behavior of the reflectivity curve as a function of theta. Is it clear?
Yes, I got it now.
Okay, but here we have theta transmission. I don't like it because it is not easy to measure it or impossible to measure it. So I should get rid of it. Now we have this one. So instead of sinus theta transmission, I use this expression. How to do that? Let me clean this and try to do that. It is a little bit long as much as I remember, but let me remember and let me get this expression. Sinus squared theta plus cosine squared theta are equal to 1, right? Here, let's consider this is the sinus squared transmission, cosine squared transmission. And if you take sinus squared transmission from this expression, it will be equal to 1 minus cosine squared transmission. And if you would like to get the sinus theta transmission, you need square root of this expression. Then sinus theta transmission will be equal to square root of 1 minus cosine squared theta transmission. Right? So what about the cosine squared transmission? If you take the square of this equation, just take the square of this equation, n is 1, cosine squared theta incident is equal to n medium square times cosine squared theta transmission. If you take the cosine squared theta transmission, cosine squared theta transmission is equal to cosine squared theta incident and medium square. And take this expression, use it here, then you can get expression in terms of theta incident, okay, within this equation. Okay, you can use it here and also here. Just use this expression. And here we have n air, it is 1, it is 1. Then here we have sinus theta incident, sinus theta incident. And on the right side, if you do these calculations, you can get square root of n square minus cosine square theta incident. And here we have the positive sign of the same term. Then we have Neve expression for the Fresnel reflection coefficient and depends on the theta incident, okay? So this is the constant for certain material, and here changing parameter is the theta incident, okay? And I know what is theta incident. Theta incident is this one, okay? So here we have n square. N is given with this one, 1 minus delta. If you neglect the absorptions, if you take the square of this one, you will get this one. 1 square minus 2 delta plus delta square. But delta is also a very small number. Then the square of this small number is also very small. You can neglect this one. Then n medium square can be written with this form. Okay, here we have 2 delta. Instead of 2 delta, I can use theta critical square, which we have got this expression in the previous transparencies, and then n medium square can be written with this form, minus theta critical square. So incident angle is very small. If theta is very small, then sinus theta for very small angles can be written with this form, theta, okay? For very small theta angles, sinus theta is equal to theta. So instead of sinus theta here, I can use theta incident. Here again, theta incident. So here we have n square. And you can use this n square here and here. It is clear, I think. And instead of sinus theta, you can use theta incident. Instead of sinus theta incident, you can use theta incident, okay? Because theta is very small. And for the cosine theta incident, for very small theta angles, you can write it like this, okay? If you take the square of it, then you can get cosine square theta incident, okay? Just also use this one here. Then finally, you will get this expression, theta incident here on the right side, theta square incident, which comes from the Taylor series, and also the square of the critical angle, which comes from this one. Okay, here we have a negative sign, okay, and now we have negative sign. And here we have a negative sign in front of the cosine square theta, but here we have positive theta square, because here we have a negative number. If you take the square of this one, you will get this expression, 1 square minus 2 theta incident square half, right, plus theta incident power 4. This is very small number because theta is already very small. Then you can neglect this one. So then you will have 1 minus theta incident square. So here we have minus sign. Here we have also minus sign. Then here we have a positive number. So finally, you have this expression for the Fresnel reflection coefficient. So it depends on only theta incident and also the critical angle. So what about the reflection? Reflection or intensity goes to detector is given by the square of the modulus of the reflection coefficient. So intensity goes to detector or reflection is given with this expression. So we have already calculated the Fresnel reflection coefficient. Just use this one here, okay? Then we have this one. If you take the absorption into account, then you can get this expression. What we have here, we have the absorption. Here in this part, we have n and n square. We have neglected absorption here, but you can also include the absorption within the calculations. Then you will have this expression within the reflection data. Now I have the reflection. Now I have intensity as a function of theta. What is theta? This is the theta or 2 theta, okay? This is the intensity or reflection. And I know that X-ray reflectivity curve is like this. So now I can calculate the reflection or intensity as a function of theta, okay? Now I can simulate the reflectivity curves. Here I have theta critical, okay? I can also express this reflection in terms of Q instead of theta. In the previous lectures, we have learned that this Q is given with 4 pi over lambda sinus theta, okay? And for very small theta angles, this equation can be written in this form. Okay, sinus theta is equal to theta for very small angles. Then just take theta from this expression, which is given with Q times lambda over 4 pi. Okay, just take this theta and use it here, and instead of theta critical, again you can use theta critical and Q critical in this case. So then you can write this reflection or intensity read by detector in this form in terms of Q and Q critical. Then what about the reflection as a function of Q or as a function of theta? So here we have absolute reflectivity or intensity at the detector, and this is the Q, okay? Or you can consider theta or 2 theta, it doesn't matter. So we have three conditions. Before the critical angle, if the Q is smaller than the critical angle, or if theta is smaller than the theta critical, then we have total external reflection. So the whole intensity goes to the detector, okay? We have maximum intensity. So we have this condition for very small angles, theta angles, lower than the critical angle, then all intensity goes to the detector. And if theta is equal to theta critical, or Q is equal to critical Q, then reflection is reduced excessively. So here, until the critical angle, this is the Q critical, or you can say theta critical, until the critical angle, we have maximum intensity, maximum reflection goes to the detector, and at this point, reflection is reduced excessively, and after this part, when the Q is bigger than 3 Q critical, or theta is bigger than 3 theta critical, reflection decreases with 1 over power 4 of Q, or 1 over power 4 of theta, you can say. Okay, so this is the reflection. What do you see here? Let me talk about reflection and theta relation. We are talking about this part. So let's consider theta is 1. Then what about 1 over theta power 4? This is 1. And for theta is 2. This is 2 power 4. Okay. And for theta is 3. This goes 1 over 3 power 4. Okay. So it decreases in this behavior, this power 4. Okay, this is the explanation of the shape of the reflectivity curve as a function of the Q or theta. Okay, any question here?
Teacher, I just have a small question. Here we are considering the surface is straight, right? I mean, it's not curved or it's not parabola. I mean, if we get curved or parabola, we're gonna get totally different results, or?
Okay, we are talking about the thin films with flat surfaces, okay? But of course, in real cases, we always have some roughness on the surface, and this roughness, of course, reduces the intensity at the detector. I will talk about this, but the surface is more or less flat, okay? We are not talking about other conditions.
All right, okay.
Now let's discuss the determination of layer thickness. So what happens to the reflectivity curve if layer thickness changes? Okay, so for incident angles greater than theta critical, then X-rays can penetrate the material. We have already discussed before the theta critical, the whole incoming X-rays are reflected from the surface, then total external reflection condition occurs. So, but if the theta incident is bigger than the theta critical, then reflection occurs from the lower and upper surfaces of the films. Let me explain by drawing the figure here. Let's say this is the silicium substrate, and this is, let's say, platinum single layer, and one X-ray is reflected from the surface of the platinum, and another one is reflected from the bottom surface of the platinum. Look at the thickness. This has certain thickness, okay? And this has certain theta angle. So remember the Brecht's law and lambda to the sinus theta. Here, instead of D, just use thickness of the platinum for this Brecht condition, okay? So theta changes. For some theta angles, we will have constructive interference at the detector, and for some theta angles, we will have destructive interference. Okay, then the interference of X-rays reflected from the lower and upper surfaces produces periodically repeating interference fringes. This is called as Kissick fringes. We are talking about this type of behavior. So you can consider constructive interference, destructive interference, constructive, destructive, constructive, destructive, depending on the theta angle. So reflection from ideal flat surfaces is calculated with Fresnel reflection coefficient. Reflection from multi-layer films is calculated by the method developed by Parrott. So if you have a single layer like this one, from the X-ray reflectivity data, you can easily calculate the thickness. How? Let me show you. This is the intensity. This is the 2 theta. Okay, this is the reflectivity curve. So here we have delta 2 theta, or between two neighboring minima, here we have delta 2 theta, or here between two maxima we have delta 2 theta. Okay, it doesn't matter. If you have a single layer on a substrate, then just get the delta theta from delta 2 theta, and then just get the sinus delta theta. And remember the Brecht's law, and lambda to d, instead of sinus theta, just use sinus delta theta. Okay, you know from the measurement, you know the wavelength of the light, and you can calculate thickness of the film, okay, by using this formula. Since this delta theta is very small, you can also write it like this, to the delta theta. Delta theta is theta m plus 1 minus theta m. Okay, is it clear?
Yes, clear.
So if you have a single layer like platinum on a silicon surface or iron on magnesium oxide surface, if you have a single layer, it is easy to calculate the thickness of the film by using this Brecht law. Okay, but if you have a multi-layer like this, silicium substrate here, platinum here, iron here, and then another platinum, let's say, okay, then in this case we have 1, 2, 3 layers. This is a multi-layer thin film, and this method cannot help you. Okay, you have to use Parrott formalism to calculate the individual layers of the films within the multi-layer thin film. Then you can calculate the thickness of each layer within the material. And this Parrott formalism is used in commercial X-ray reflectivity simulation programs. You can also produce a simulation program by yourself by using the Parrott formalism. Then let me continue with the effect of the film thickness on reflectivity curve. Here we have two samples. Blue one is gold. Roughness of gold is 2 angstrom. And this is the thickness of the gold. Thickness of the gold is 120 angstrom. And we have another thin film, which is also gold, but thickness is 40 angstrom. Everything is same, but just the thickness is changed. Then roughness of the gold also 2 angstrom in this case. Okay, we have same material, gold here and gold here, and same roughness 2 angstrom here. They have same electron densities, and we are using the same instrument. The only different parameter is the thickness of these two materials. So what happens to the reflectivity curve? This is the theta to theta or Q axis. This is the reflectivity or intensity axis. Okay, so what do you see? The curve from the thinner gold, we have this red curve, and the thin film from the thicker gold, we have this blue curve, this one. What do you see here? That the distance between the oscillations in thinner film is bigger than the distance between the oscillations in thicker gold film. Why? Just remember the Brecht's law to the sinus theta. If you consider that this is thickness of the film, if this is smaller, then this delta theta between the oscillations will be bigger. So here we have thinner film, then we have bigger delta theta between the oscillations. Okay, we have thicker film here, we have smaller delta theta between the oscillations. By using this Brecht's law, you can get this weave. I have to tell you something more related to this one. What do you see here? Look at the total intensity from the blue curve, thicker gold, and look at the total intensity from the red curve. So the intensity, total intensity or total reflection from the blue curve is bigger than the total intensity or reflection from the red curve. Why? Because in case of blue one, we have the thickness 120 angstrom. Here we have the thickness is 40 angstrom. Okay, so here we have atomic layers, several atomic layers, okay, and each layer reflects the incoming X-rays to the detector. You can consider like this. You have many mirrors. You can consider each layer as a mirror, and they reflect the incoming X-rays to the detector. So here, let's say you have 20 atomic layer, but here we have 60 atomic layer. Many atomic layers compared to the thinner film. So then this reflects more X-rays to the detector, okay, compared to the thinner film. So then the total intensity reflection goes to the detector from the thicker gold film is bigger than the total intensity goes from the thinner film. Now let's discuss the determination of electron density from the X-ray reflectivity curve. We have already showed that the critical angle has this type of relation with the delta, and delta includes electron density. Then I can write the relation between critical angle and electron density. Okay, so then if you have bigger electron density in the material, then you will have bigger critical angle. If we have lower electron density, then we will have lower critical angle, okay? Because this lambda is fixed, incoming wavelength, this classical electron radius is a constant, pi is a constant, so only electron density affects the critical angle here on the left side. So now let's have a look the effect of the electron densities on the X-ray reflectivity curve. Here again you see two curves, red one and blue one. Let's start with the blue one again. What is blue one? Aluminum. Here we have aluminum. The thickness of the aluminum is 40 angstrom, and the roughness of the aluminum is 2 angstrom. This is the roughness. And here we have a substrate, silicium. And this roughness between silicium and aluminum is 0. We have very perfect surface. We have perfect surface without any roughness. Here we have roughness of the surface of the aluminum, which is given with 2 angstrom. Okay, then let's have a look. This red one, this is also grown on silicium. We have silicium substrate, and on top of it, we have gold. What about the thickness? Thickness is same, 40 angstrom. And what about the roughness? Roughness of the surface for the gold is also 2 angstrom. And the interface roughness between the silicium and gold is 0. We have very nice, very smooth surface. Okay. Then what about the X-ray reflectivity curve? This comes from the gold. This comes from the aluminum. Okay. So what do you see here? We have same thickness, but what about the total intensity? Total intensity comes from the gold is much bigger than the total intensity comes from the aluminum. It is strange. And what about the distance between the oscillations? Here we have delta theta or delta Q. Okay, look at this one, delta theta or delta Q, and look at this delta theta from the blue one, or delta theta here, delta theta here. So they have same delta theta. Delta theta does not change because they have same thickness. Okay, but the total intensity dropped a lot. In addition to that, look at the critical angle. In case of blue curve, comes from the aluminum, we have very small critical angle. In case of gold, we have much bigger critical angle. So I can write like this: the critical angle of the gold film is bigger than the critical angle of the aluminum film. Okay, why? Because critical angle is related to the electron density. Gold contains more electrons. Okay, remember the periodic table, remember the atomic number of the gold, and remember the atomic number of the aluminum. Aluminum is much smaller atom compared to the gold, and gold contains more electrons. So electron density of the gold is much higher compared to the aluminum. Then critical angle changes in the X-ray reflectivity curve. But why intensity is less? They have same thickness, okay, but we have less intensity from the aluminum. It is related to electron density again. What is the X-ray matter interaction? X-rays are interacting with the electrons within the matter, okay? So if you have more electrons, each electron will behave as scattering center for the incoming X-rays. So if you have more electrons, then you can able to send more X-rays to the detector. So since within the gold we have more electrons, then we can send more photons to the detector. Then the total intensity coming from the gold is much bigger compared to the total intensity coming from the aluminum. Then let's continue with the determination of roughness. So what is the effect of the surface roughness? What is the effect of the interface roughness in thin films in X-ray reflectivity curves? So in real measurements, the surfaces and or interfaces of thin films are not smooth. So here we have considered that this surface has certain roughness, this surface has certain roughness, but we have considered that this is smooth. But in reality, this is not the case. Usually we have also roughness here. But of course, you can decrease the amount of the roughness by using special sample preparation methods. But now we will discuss the effect of the roughness. So what is the effect of the roughness? Just consider that here we have very flat surface of the film. Let's consider these are the atoms at the surface of the film. So we send X-rays from the X-ray source, they go to the detector. If you have perfect alignment of the atoms, then this surface behaves like a mirror, perfect mirror without any roughness, okay? But if you have such surface, these are atoms again, but now surface is not perfect. Look at the surface. Surface is rough. And now I am sending X-rays. So only small portion of the X-rays can reach the detector. Okay. Then if you have a rough surface, the intensity at the detector will be lower. Okay. Due to the diffuse or off-specular scattering. These are diffuse scattering, okay, or off-specular scattering. Only this one is specular reflection, okay? So this is the effect of the roughness in real applications. So then the intensity of Kissick fringes and the intensity of the entire reflection curve will decrease. We will discuss this one. We have calculated Fresnel reflection coefficient for ideal flat surfaces. But if you consider roughness, then what about the reflection from the rough surfaces? So you have to consider this part here, E over minus Q square times sigma square over 2. So what is Q? This is theta, okay? Angle or scattering vector. You can use both of them. So here we have sigma. Sigma is the roughness. And Q includes theta, okay? So what do you see here? If you have zero roughness, then this R rough will be equal to R flat, okay? If the sigma is zero, if we don't have any roughness, then we have reflection from the flat surface. But whenever you have roughness, this intensity at the detector will decrease, okay? With this term here. But in addition to that, here we have Q square or theta square, okay? So what do you see here? At higher angles, if this Q is bigger or theta is bigger, it means that at higher angles, the effect of the roughness is dominant. You asked me this question, why these oscillations disappear earlier in case of this one? Okay, but look at the amplitude of the oscillations in the blue one. Here we have, in the blue one, we have huge oscillations, huge amplitude of the oscillations, and this amplitude decreases with the angle. And look at the red one, we have huge oscillations at lower angles, and this amplitude of the oscillations disappears at higher angles. This is due to the effect of the roughness. Because with this formula, E over Q square, roughness square over half, okay? So if you increase this Q, then this term will decrease the intensity goes to the detector. And at higher angles, this term will be very dominant, and then the amplitude of the oscillations will be lost finally. You will see more or less nothing after a certain angle, okay? So for this reason, the amplitude is decreasing by the angle. So this is the effect of the roughness. So now let's discuss the effect of film roughness on reflectivity curve. Here again, we have two films. Red one is gold, thickness is 40 angstrom. Blue one is also gold, and thickness is 40 angstrom. So they have same electron density, same thickness, and they are grown on silicon substrate, and both of them has zero roughness on the surface of the silicon. But the only thing is that this red gold has lower roughness compared to the blue gold, okay, blue curve here. So what about the result? They have same electron density, then they should have same critical angle because we are talking about the same material. So what you see here that they have same critical angle and they have same thickness. Look at the delta theta here. Look at the delta theta in case of blue curve. So we have same delta theta because they have same thickness, okay, and lambda to the delta theta or sinus delta theta. So since they have same thickness, we should have same delta theta. Okay, we see this one, but the only thing is different here that the roughness. So what do you see here? In the case of red one, the amplitude of the oscillations decreases by angle, okay, because we have roughness 2 angstrom, and at higher angles we cannot see any amplitude, we cannot see oscillations due to the roughness. But in case of blue curve, this amplitude disappears at lower angles compared to the red one because the roughness of the gold in the blue curve is much higher compared to the roughness of the gold in the red curve. And remember this formula, Q square sigma square half, okay? So we have some certain roughness, and at higher angles, at higher Q values, at higher theta values, this term becomes very dominant, and then you can completely lose the amplitude of the oscillations. And let me continue with the substrate roughness. In the previous case, we have discussed film roughness, and we didn't have any roughness on the substrate. But here we have same thickness of gold and same roughness of golds. And here we have different roughnesses on the substrate. Okay, so here we have 0 roughness on the blue one, and here we have 1 angstrom roughness on the red one. So what happens? They have same thickness, they have same delta theta or delta Q values, okay? And what about the critical angle? Critical angle is same because they have same electron density. We are talking about same gold material. And what happens at higher angles? Intensity drops suddenly in case of the rough surface of the substrate. So why it happens at higher angles? Of course, it is related to the formula which we have discussed here, E over Q square sigma square. So at higher Q values, at higher angles, this term will be dominant, okay? But in real cases, what happens within the material? So you send the X-rays with some certain angle. If you send X-rays with smaller incident angles, X-rays cannot penetrate into the substrate. And if you send them with higher theta angles or with higher Q values, they will able to enter also into the silicium substrate, okay? Then the effect of the silicium surface can be seen at higher angles, okay? At lower angles, we cannot see it. So whenever X-rays start to enter into the silicium substrate, and they can get the information from the roughness of the substrate. Let me finish my lecture with real experimental data and their simulation, and you will see how this method is powerful. So what we have here, this is magnesium oxide substrate, and we have iron layer with the thickness of 22 nanometer. And here we have cobalt oxide layer with the thickness of 10 nanometer. Okay, so these are the nominal thicknesses. So then we have this reflectivity curve here. Okay, reflectivity curve as a function of angle or Q. This is the intensity. So when we have done a simulation of this real experimental data, we found this thickness values, this roughness values, and those electron density values. Okay, what do you see here? Magnesium oxide, you cannot measure the thickness of the magnesium oxide because X-rays can measure the thicknesses up to more or less 400 nanometer, and this magnesium oxide thickness is about 1 millimeter or 0.5 millimeter, let's say. Okay, so you cannot measure the thickness of the substrate, and we have thickness of the iron here, 22 nanometer, and this is the thickness of the cobalt oxide. By simulating this experimental data, you can get this one. We have used Parrot formalism to simulate this bilayer system. And what about the roughness? This is the roughness of the MgO surface here, 0.13 nanometer or 1.3 angstrom. And this is the roughness of the iron surface, 1.1 angstrom. And this is the roughness of the cobalt oxide. This is 2.3 angstrom. Okay, much bigger roughness compared to the iron and MgO. And what about the electron densities? This is the electron density you can find from the tables in the internet or books, which belongs to the MgO, pure MgO crystal. And this is the electron density of the pure iron crystal. And look at the electron density of the cobalt oxide. In tables, if you have 50% cobalt, 50% oxygen, cobalt 1, oxygen 1, then you should have electron density, as much as I remember, around 6.4 gram per cubic centimeter. Okay, but here we have found 5.4, which is lower than this one. Why this cobalt oxide has lower electron density? If you write here in the simulation, instead of 5.4, if you write 6.4, you cannot fit this data. The simulation will be completely different. Okay, we have done it, but this data, this number fits the experimental data. But why this is lower than 6.4? Why it is 5.4? Why we have lower electron density from the cobalt oxide layer? Because during the thin film growth, you would like to get cobalt 1, oxygen 1, okay? 50% cobalt, 50% oxygen. But in some cases, you can also produce cobalt 2, oxygen 3 phases within the material. You also have these ones. So then in total, our material is cobalt 3, oxygen 4, okay? So it is not a pure cobalt 1, oxygen 1. It also includes cobalt 2, oxygen 3 phases. So look at the electron density of this one. Cobalt contains many electrons, as much as I remember, 27 electrons, and oxygen contains 8 electrons. So if you have more cobalt, then you will have bigger electron density. Look at this one. Here we have more oxygen compared to this one, then you can expect lower electron density. So if you have in total this phase in the cobalt oxide layer instead of this pure cobalt 1, oxygen 1 phase, then you should expect lower electron density within the material. So just by doing this single experiment and simulation, you can get information about the homogeneity of the cobalt oxide. You can get the information about the electron density of the cobalt oxide. You can get information whether this cobalt oxide is purely consisting of cobalt oxygen phase or cobalt 2 oxygen 3 phase. So you can understand, you can get all this information from this type of experiments. And let me finish my lecture with this real example. This is titanium dioxide substrate, titanium dioxide rutile. This titanium dioxide crystal has different phases, rutile, anatase, and also brochite, as much as I remember. So then you implant this titanium dioxide with cobalt plus ions, okay? Energetic cobalt ions. We have discussed this one during the X-ray diffraction experiments during the last lecture. So then this cobalt ions have certain incoming energies, 40 kiloelectron volt, let's say, so they can enter into the material and they are stopped somewhere here. But depending on the depth of the titanium dioxide from the surface, we have different concentrations. So here we have different concentration of the cobalt. Here we have different concentration of the cobalt. Here we have different concentration of the cobalt. So since some cobalt atoms enter into the titanium dioxide, we will have different electron densities in this region, okay? So this is the simulation result. Here you see pure titanium dioxide where we don't have any cobalt ions here. Then it has this electron density. This is the electron density of the pure titanium dioxide. But in this part, more or less this thickness, we have different densities, okay? Depending on the concentration of the cobalt within this region, then here we have experimental data with circles, and here we have the red curve, the simulation. So with this simulation, I can get that the first layer on top of this titanium dioxide, which has thickness of 11.2 nanometer, this has this electron density, and this layer just below this one, second layer, has this thickness and this electron density. What do you see here? This has the highest electron density. It means that this has the highest cobalt concentration, okay? So by using this electron density, you can also produce cobalt concentration profile. This is the depth, this is the surface of the titanium dioxide, and here we have the cobalt concentration, let's say, cobalt concentration. So you can get this type of behavior. And in this part, we don't have any cobalt within the titanium dioxide. So what do you see here? This number is increases and then goes down and reaches to the pure titanium dioxide electron density. Okay, so by using the X-ray reflectivity and simulating the experimental data, you can also get this information from your sample. This is unique, very nice data and application of X-ray reflectivity. Okay, with this one, I finish my lecture. Then we have learned X-ray reflectivity today, and we have learned the effect of the thickness, effect of the electron density, effect of the substrate roughness, effect of the film roughness, effect of the interface roughnesses on the X-ray reflectivity curves. And we have learned how critical angle is related to the electron density. We have learned why X-ray reflectivity curve intensity changes as a function of the theta or Q by using the Fresnel reflection coefficient. We have calculated all these things, and then we have finished with real examples. And next week, I would like to continue with absorption experiments. So take care of yourself. Bye-bye.